Hello. In the last of these videos, I introduced an alternative way of thinking about these random variables. In particular, I noted that we can write random variables of most types, for example the sample mean on the left-hand side of the expression shown here, as shown on the right-hand side. In this sum, the first term is the expectation of the random variable, which is a scalar-valued constant. The randomness is then accounted for within the random variable delta, which has expectation 0 and can be positive or negative. I explained this expression using the diagram shown here. The horizontal line here represents the real axis. The vertical line then indicates the value of the expectation, which is fixed and not random. The true value of the sample variable, of the random variable x bar, might be here, in which case delta is as indicated here. The random variable is random, however, and it can thus be at a range of different points on the axis. For example, it might be here. In this case, delta is negative, as is indicated by the arrow shown here. I have mentioned this again because in this video we're going to consider how this method can be used to derive estimators for the parameters of random variables. To see how, suppose that I have generated a series of random variables from a distribution and plotted them as shown here. Now suppose that I know the expectation of this distribution and that this expectation is indicated using the red dashed line shown here. If I know the expectation of the distribution, then it stands to reason that I can calculate a delta value from each of the random variables I generated using the expression shown at the top of the slide. These delta values, which notice are both positive and negative, are illustrated using the green arrows here. Now let's suppose that I can calculate the average of the square of these delta values. I would do this using the expression that has just appeared. It is straightforward to demonstrate that this is an estimator for the second moment of delta. To prove this, all I need to do is replace the random variable x here by the expectation of this random variable plus delta. Once I do this, the two expectations cancel, and I thus arrive at an estimator for the second moment of the random variable delta as promised. Notice that we estimate the second moment of delta here, as we know this is guaranteed to be positive. The first moment of delta is uninteresting, as we know that it is 0. To see how this idea can be used to estimate the parameters of this distribution, I want you to watch the movie, which will appear in a moment. The panel on the left here indicates a set of random variables that have been sampled. The red line here is the true expectation of the distribution that was sampled. During the movie, a green line will appear here in the panel on the right. This is the value of a variable called mu, which, as you can see, is what is plotted on the x-axis of the graph in the right panel. The y-axis on this right panel graph is then the sum of the squares of the distance between each of the random variables that have been generated and this mu value. During the movie, and to make this clearer, a green dot will appear which will indicate the value of this sum for the particular value of mu that is indicated by the green line in the left panel. Here is the movie. What you can see in this movie is that the sum of squares of the differences is small when the green line is in the center of the cloud of random variables. In other words, as the mu value moves away from this central position, the sum of squares that appears on the right panel increases. The graph of this function, mu, is thus quadratic, as shown on the right. Furthermore, this single minimum in this quadratic is the midpoint of the distribution. In the still image that has replaced the movie, the position of the midpoint is indicated using a green line in the panels on the right and left. Notice that this green line appears close to the red line that indicates the position of the true expectation. It is not, however, exactly equal to the true expectation. If we return to the equations on the previous slide here, we can see why this green line is significant. Recall that on the previous slide we discussed how the expression on the y-axis of the right graph in the image is an estimator for the second moment of the distribution of the random variable delta. The green line is significant as this line is drawn at the value of mu at which the quantity plotted on the y-axis is minimized. This idea thus provides us an alternative method for estimating the expectation of a distribution. If you work through the maths, you find that the sample mean is the estimator of the expectation that minimizes this sum of squares of the delta values. You can use this idea to calculate the parameters of the underlying distributions of random variables. To see how, let's suppose that we are told that each of the xi is a sample of a Bernoulli random variable. We know that the expectation of a Bernoulli random variable is p, and we can thus insert p in place of the expectation. We then want to find the value of p that minimizes this quantity. We thus differentiate the expression with respect to p to give the following. Then, as we are at a minimum, we set the derivative equal to 0. With a little rearranging, we thus arrive at the following least squares estimator for the parameter of the Bernoulli random variable, which is just the sample mean again. The steps for this procedure are thus to insert the expression for the expectation into the expression for s squared. You then differentiate with respect to the parameter, set the derivative equal to 0, and thus minimize to get an expression for the parameter of the distribution. This method will not always work, however. You may well find that there are distributions that do not have a minimum in the graph of s squared versus the parameters. In the quiz that follows, however, you will have a few opportunities to try the method in cases where it does work. Good luck with those, and as always, thank you for your attention.